first time. Vijay, go. You find your number in the schedule and your name on the title of the file. You click twice and launch it to presentation style. If by some reason movies are not working, do not panic, explain them by waving hands. They should work, but just be more ready to anything unexpected.
What are we grading out of? What are we grading out of?
First?
No, so, like 1 to 10, like 1 to 5.
A, B, C.
Oh, okay.
More questions? If no, let me invite to the stage Master of Science, Vijay Shah, who has recently completed his degree, and he will present computational modeling of the interface between silver and silicon. Floor is yours.
All right, thank you for the introduction. As Professor Keeling said, I'm Vijay Shah, and I'm going to be modeling the interface between silver and silicon nanoparticles. So, nanoparticles are small materials that consist of, in the case of our simulations, an inorganic core, meaning that the material or the atoms that the core is made out of are not made out of carbon, hydrogen, etc. Rather, they're made of silicon and silver in our simulations. Each of these nanoparticles are covered in different types of chains made up of carbon, nitrogen, and hydrogen atoms. And nanoparticles have been shown to exhibit size-dependent properties, in particular optical and electrical properties. So optical properties include both photoluminescence and surface plasmon absorption. And surface plasmon absorption allows the nanoparticle dispersions to exhibit different colors when they're viewed with different types of experimental apparatuses. And for electrical properties, the organic chains covering the nanoparticles can actually hinder the conductance of the nanoparticles. And overall, there are many practical applications of nanoparticles, including to photovoltaic cells. So the objective of our research is to determine the best electron donor and best electron acceptor, and use this pair in order to help facilitate the charge transfer between nanoparticles. So in particular, we will be looking at the density of states, the absorption spectrum, and partial charge density in order to characterize the charge transfer between different states of our nanoparticles. So on this slide, you can see a couple of different images for our model. So on the left-hand side, we have a silicon nanoparticle. The yellow atoms are representing the silicon atoms, and the turquoise atoms represent the carbons, and the gray atoms represent the hydrogens. On the right-hand side, you see a silver nanoparticle, where now the pink atoms represent the silver atoms, and the chains are made up of different molecules such as carbon, hydrogen, nitrogen, and oxygen. And for the purpose of our simulations, which were run in VASP, the silver and hybrid models were oxidized 5 times. So this means that from the neutral model, we actually removed 5 electrons from the model when we were running simulations on them. And this was to explore different oxidized states for our model. But for the purpose of this talk, I'm only going to be talking about the simulations where we removed 5 electrons. So here on this slide, you can see 2 more different models, one being where some of the organic chains are removed from both of the nanoparticles. And on the right-hand side, you see a large ligand connected to the silicon nanoparticle. And both of these are different morphologies than when we just consider the silicon nanoparticle and the silver nanoparticle, as well as when we take both of these models and place them in the same input file. So we were really looking at 5 different models, 2 lone nanoparticles, then both of the nanoparticles brought together, both of the nanoparticles moved closer to each other in order to model the interface between these nanoparticles, and finally, where we have a long ligand attached to the silicon nanoparticle. So on this slide, there's a quick movie. It's going to be very difficult to see, but this is optimization of the silicon nanoparticle by itself. So this was run using, I think, 1,000 ionic steps in VASP in order to optimize the silicon nanoparticle. And you can see the total energy after optimization, as well as both the alpha and beta orbital band gap. So the alpha represents the band gap between, or for the red states in the density of states, whereas beta represents the filled blue states and all of the states below 0 on the vertical axis. And then finally the Fermi energy as well. So we can see that there are some electrons in the conduction band here, and this is likely because the model was not oxidized. So further work could be done in order to actually oxidize the lone silicon nanoparticle and remove electrons from the conduction band. And we'll see a consequence of not oxidizing this model in a couple of slides. Here on this slide, this is the density of states for the silver nanoparticles. So we did oxidize this model 5 times. And you can see, again, the energy after optimization, as well as alpha and beta band gaps. You can see that there are, again, electrons in the conduction band. And finally, Fermi energy as well. And on this slide, here's a model where we took both nanoparticles and put them in the same simulation and optimized the entire model at once. So we have both of the nanoparticles are being optimized at the same time, and the total energy after optimization is actually a little bit higher than the separate energies after optimization for the silicon nanoparticle and the silver nanoparticle, which signifies that the binding energy is actually positive, and therefore the 2 nanoparticles would want to actually repel each other when brought close together. And again, we have density of states here. You can see that there's not really a distinct difference between the valence and conduction bands in the density of states. The highest occupied states are very close to the lowest unoccupied states. So on this slide, we have a couple of different absorption spectrum, and for the first 3 plots, there's a very large peak near 0 energy, signifying that incident light would have to have a very large wavelength in order for an electron to move to a higher energy state. And then on this lower right-hand plot, you can see that there are peaks at a higher transition energy, signifying that ultraviolet light can actually excite electrons from a lower state to a higher state when these electrons absorb photons. And here on this slide, you can see a couple of charge transfer plots. So on this left-hand side, these are the charge transfer plots for the HOMO and LUMO orbitals. And then on this model on the lower left-hand side, we have the HOMO orbital is represented by pink, and the LUMO orbital is represented by gray. And on the right-hand side, we see that there is some charge transfer between HOMO -4 and LUMO +5. However, there still is not too much. So further work could be done in order to actually characterize different morphologies and different oxidations and determine where the most charge transfer will actually occur, for which models they will actually occur in. So in conclusion, we see that the density of states, absorption spectra, and partial charge density plots do not actually help in facilitating the charge transfer between states when our models have 5 electrons removed from them. And in the future, work could be done in order to determine which morphologies and oxidations will actually yield the most charge transfer between states. So with that, I would like to thank Professor Dmitry Killing, Dr. Yulan Han, Aaron 40, and Nerskin USD cluster for computational resources. Thank you.
Okay, but thank you, guys. So there is time for a couple of questions. I have one. So what is the reason for absorption close to zero energy, and do you see, if it is not real, what are the practical ways to remove this artifact?
Yeah, so I'll go back to the plots, yeah, right here. So the question was what the significance is of this absorption spectra looking, basically having a peak at zero, how it could be removed, and if it's real or not. So the peaks near zero, right here in the spectra, were actually a consequence of having the HOMO and LUMO states be very close to each other. So the band gap was essentially zero, which means that electrons did not need to have much energy in order to go from one state to the next state when you're trying to excite the electrons. And in order to actually combat this, one would need to oxidize the model more, or in other words, remove more electrons from the model in order to have these peaks appear at higher transition energies.
Can you go back?
Yep.
More? Yes. So probably you wanted to repeat the same verbal explanation about this figure.
Right, yeah, so here we can see, as well from this figure, you see that HOMO and LUMO are very close to each other, so the band gap's essentially zero, and the same thing actually occurs right here. So you can see that this final state that is occupied is only partially occupied, and right next to it is an unoccupied state. And similarly, in the beta orbitals, there's a partially occupied state right here around negative 7.5 electron volts. And then finally, for the silicon nanoparticle by itself, again, there's a partially occupied state in the alpha orbital. And then very close to it, you see that there's a completely unoccupied state. So those would cause the absorption spectra to have peaks at low energy.
Okay.
Did you look on the localization of HOMO-LUMO in that system? Is the HOMO-LUMO in the same system or in different quantum dots?
Yeah, so we did consider I did do a simulation where this model was actually not spin polarized.
Not this one, I mean next one.
Oh, the next one?
Two system, yeah, I mean two.
Yeah, so yeah, we didn't actually, I didn't actually have time to consider the original model and determine like the original HOMO and LUMO for this system. That would have been something that would have been good to compare to though.
And what is the distance between these two silver nanoparticle and silicon particle?
It's very low, I believe.
No, I mean, yeah, and the two model system, two
yeah.
pair system. I forget the other one.
Here we go. Yeah, so are you talking about like center to center distance, surface to surface separation?
Surface to surface.
Okay. I believe that was approximately 5 angstroms. It was somewhere between 5 and 10 angstroms.
So do you think that they're supposed to have any interaction between the in that distance? Any charge transfer possibility?
Charge transfer, most likely not. But yeah, interactions like binding energy, that would be present. So binding energy would be a little bit positive or a little bit negative at that distance.
Yeah.
Okay. If there are no more questions, well, thank you, Vijay, once again. And let me invite to the stage Landon Johnson, whose presentation title is so long that I cannot pronounce it. So it's very, very technical. But to my understanding, he's continuing the discussion of interface between donor and acceptor groups. And he's looking how the ability of charge transfer depends on the linker between them.
Yes, that is exactly what I'll be talking about. So specifically, I'm going to be looking at the boundary between cesium, lead, bromide, peroxide, and 2 different types of titanium dioxide. So I guess why am I looking at this? In order to make a solar cell out of perovskite, you essentially need to surround it with a hole transport material and an electron transport material. The reason for that is that, I mean, if you shine light on a perovskite, cause excitations, that's all fine and good, but you're not going to end up getting any current. You're not going to be able to build a potential difference between your two terminals unless there's an inherent preference for the direction of that current. So what you want to do is set up a system so that when you do create excitations, the electrons will naturally want to flow one direction and the holes will naturally want to flow to the other direction. So in particular, I'm looking at this interface here. So these are the two models that I'm working with. We've got the titanium dioxide on the top and the perovskite on the bottom. And we have a isopropanol linker group in this case, and we have hydroxyl linker groups in this case. And we're just looking at the differences between these and just trying to characterize them generally. So these are some densities of states, I guess, of the separated systems and then combined. So these are all the isopropanol model, and these are all the hydroxyl model. So the perovskite in both cases are essentially identical. There are some slight differences between the titanium dioxide, but largely they have the same structure. You can see that when you do combine these systems, you actually get a different shape, I guess, of the density of states. You end up losing a lot of these states from the titanium dioxide. It suggests that there is a significant interaction between the two when you put them close together. So some of the things that I can pull from that data are just the total energies of each system, the HOMO and LUMO gap, the Fermi energy. And we can see that in both cases, you do actually reduce the HOMO-LUMO gap. But in the hydroxyl case, we see that there is actually a smaller gap, which means that you'll be able to get a wider frequency of solar radiation that you could potentially convert into electric current. When I calculated these out, this one was like 494 nanometer wavelength, I believe, and this one was 430 something. So it's not a huge difference, but it suggests that there is at least something of a difference there. So these are just some plots of orbitals, and then these are one-dimensional potentials that are obtained by integrating over the X and Y dimensions just to yield essentially a one-dimensional probability of finding an electron in some region. So in the isopropanol case, you can see that I guess you can't really see that. So these are the, I can't remember which is which. I think it's the same between them. The blue orbitals are is the HOMO. The red ones are the LUMO. And you can see that those are both localized on the titanium dioxide in the isopropanol case, whereas in the hydroxyl case, you actually do have you have the HOMO in the perovskite, and then the LUMO would be found in the titanium dioxide. This would be preferable because as you do create an excitation, if the electron jumps into the next orbital, it will actually move over to the titanium dioxide, whereas in this case, the charge doesn't actually end up going anywhere, so you don't get that desired property that we're looking for. So this suggests that the hydroxyl is probably better in that regard as well. This is kind of a schematic of what I was just talking about, where the lowest energy jump would be just from titanium dioxide to itself, whereas in this case, you would actually transfer the charge over to the titanium dioxide from the perovskite. So I was only able to get one of my molecular dynamics jobs to run without failing immediately. And this is the density of states after doing molecular dynamics at 1000 Kelvin for, I think, like 329 femtoseconds. So I guess the general shape of the density of states doesn't change that much. You just kind of get more states over in the conduction band. But it does actually seem to increase the range over which you can actually get absorption. You kind of end up getting this whole bit here that doesn't make an appearance in this end. And these two density of states are the same ones from before. Yeah, I guess I don't really know what else to say about that at the moment. And this is the movie of that molecular dynamics run, I guess. So, in conclusion, the evidence does seem to suggest that the hydroxyl model is the more suitable model for photovoltaic applications. Just because you do have a smaller energy gap, you do have actually charge transfer happening, or at least it's more likely to be happening. I feel like there's one other thing, but I can't remember what it is right now.
Okay, then the last thing is to round up. Any question? Yes.
I have just technical questions. I was not able to understand what is your really. Can you show me on this structure? What is your hydroxyls and what is your isopropanes? Is it ligands on a?
Yeah, it's strictly
ligands on a. The surface is your titanium dioxide surface, right? And the quantum dot is your perovskite, or backward. Which one is which one? I'm completely confused.
Which?
What is your quantum, like, the fine structure? What is it? Is it titanium dioxide or perovskite?
I guess I'm not sure what exactly it is that you're trying to
I'm also not sure what we're talking about. So you have a surface and you have a zero-dimensional structure. Agree?
Zero-dimensional structure?
Yeah, because it's confined from all three directions.
Okay.
No periodicity along neither of these axes, so it's zero-dimensional structure.
Okay.
What we usually call nanoparticles or quantum dots or nanocrystals. So what is your nanocrystal? Is it titanium dioxide crystal or it's a perovskite crystal?
Oh, this would be the crystalline structure. I guess I'm thinking about this as just basically taking a chunk of like a thin film.
So where is your titanium dioxide?
This is the titanium dioxide.
So you have quantum dots made from titanium dioxide.
Yes.
And
okay,
the surface is made from fumes or whatever, surfaces of perovskite.
Yes.
Then again, your orbitals, if you go back to the orbitals here, so you on the one side, your orbitals look like they're completely localized on your nanocrystal, on a nanoparticle, right? And on the second, is it like hybridized? Like you have orbitals both on the surface.
What is color codes?
So the blue in this case would represent the highest occupied orbital, I guess. I don't know if that's.
And the red?
Like the red would be the lowest unoccupied. So if
you
the
have
lowest level excitation would mean that an electron would go from the blue band to the red band.
Okay, so in the first case you have both HOMA and LUMA on your nanoparticle, and on the other case you have one being localized on the nanoparticle and the other is localized on the surface, and this is what you call a charge transfer.
Right.
But my understanding, the energy of absorption is very different between these two materials. So you can easily tune the absorption just, let's say, on the range of your perovskite or on a range of your quantum dot, because it looks like your energetically they're very different, right? So you can imagine that you're really exciting just one system rather than both of them.
Okay, so you're assuming like a fixed
like I'm
energy
assuming
that
that in the case when you have your HOMA being on one material, when your HOMA is on one material and your LUMA on the other material, this transition is optically inactive. It's you cannot excite such state because it's optically inactive, right? You can excite the states which are either both localized on a perovskite, and then it would be perovskite transition, or both localized on a quantum dot, and then this would be your quantum dot transition. And then the idea is when you excite one material, then the charge transfer should go from not between HOMA-LUMA, but kind of inside the band, from unoccupied state if it's electron transfer, or from occupied state if it's a hole transfer. Like, I don't understand your definition of a charge transfer. Looks kind of usually, and what's the purpose of, like, this charge transfer state will not provide you any good things for the current. Because your idea is that you, like, this construction of the material is based on the idea that you use one as absorption material, as a synthesizer, and the other would be your contacts. And it looks like probably the three-dimensional surface or whatever, two-dimensional surface would be your contact, right? And then your titanium dioxide would be the synthesizer in this case. And then you need a charge transfer from the titanium dioxide to the either in a both occupied state or both unoccupied states. I mean, after you optimize it, of course, you create a hole, and then hole goes. Then hole transfer means electron from one material goes to the whole state of the other material. But not like you exciting this charge transfer state, because such charge transfer state would be optically inactive.
You might have to run through that a little bit slower for me. I guess that was kind of quick. So the perovskite is the optical absorber in this case. The titanium dioxide is not in and of itself optically active.
Then what's the purpose of your titanium dioxide?
It's essentially, I guess this is sort of what you would want, is so that you have an electron in here that gets excited and you want it to get naturally pulled away from the perovskite into the titanium dioxide.
What for?
To create a current.
Current? Where?
Or potential difference.
You just create a charge on a quantum dot. That's it. It's not called current.
There would be a terminal attached to the other end.
To
the
quantum
titanium
dots?
dioxide.
To titanium dioxide quantum dots will be something like you will have some lead on a titanium dioxide.
Well, I mean, when I actually made these, I made thin films, so it wasn't necessarily like quantum dots, I guess.
I think.
I mean, physically, I guess I don't know exactly how I would make this.
You probably need really look on a Gretzel cells just to get the main concept and understand the idea why people really have this kind of molecule and the surface, or whatever, nanoparticle and the surface.
Okay.
Because I think conceptually you're really doing something not what is supposed to be for the not at least for the solar cells.
Mm-hmm.
Because again, in solar cells, the idea is that you excite in one material, right? And after excitation is done, then the charge transfer happens from that. Let's say if you excite, you have excited electron on the valence band, on the conduction band, right, of whatever, of the molecule. And then this electron will go to the, usually will go to the semiconductor, right? Which has plain kind of, the wave-like electronic structure where you really kind of creating a current, and then it goes to the leads. Or it can be hole transfer, then your hole, which means electron from titanium surface, will be taking the place of the excited hole in your molecule. So this is how the Gretzel cells works. In your kind of suggestion how these guys should work, I'm completely lost what exactly is the purpose of your titanium dioxide. And why you need really to excite, like as I said, like this excitation, which you say is good because it's a charge transfer state, it is a charge transfer state, but such state is optically inactive. Because your orbitals not really overlap, and your dipole moment for such transition should be very, very low.
Okay.
More questions? It was not a question, it was a comment.
Well, I think conceptually the idea why and what the motivation behind all these things looks kind of completely messed up.
More questions? Okay, then let's thank Landon once again. So the next presentation is the last one in the sequence of solid materials, and it is slow transition to softer materials. So it is by Daniel Ramirez, and he will tell another story about wet halide perovskite surfaces with different surface absorbers.
Thank you, Dimitri, for the kind introduction. So I will be studying same thing similar to Landon with 2D thin film perovskite, but in this case I'll be seeing the effects of two different ligands placed on such a structure. So we begin. So basically the overview, I'll just give you a little quick background, purpose, results, so on and so forth, basically standard on all this. So basically perovskites, they were discovered in 1839 in the Russian mountains by Gustav Rose, but they weren't named after him, they were named actually after a mineralogist named Lenin Perovsky. So that's where the name came from. Crystal structures normally ABX is a molecule containing ABX3. In my case, I do have the same type of structure as Landon, where I will be having a study of cesium, lead, and bromine as my ABX3 molecule. And what makes perovskites really unique and interesting is that different cations can be embedded into the structure and that allows for different types of materials. Basically, the goal is try to find that correct one that will make it flow perfectly for what we need it for. And I'll mention that in a little bit. But basically, what makes a perovskite what makes a cell is the doping, the P and N doping. And in this case, what Landon was talking about, how P types are usually electron hole carriers, and N type semiconductors are electron carriers. The thing we gotta make it flow, make it good, is have a junction where we have both the P type and N type work perfectly together. So quick little explanation. An N type, as I said, are basically electron rich. They sort of donate their electrons to the structure to make it considered an N type, so it makes the structure electron rich. And a P type semiconductor, as the little picture says, it's electron hole carrier. So whenever that electron gets full, the hole will be displaced. There will be a hole after that electron moves into there, and it will just keep repeating itself and over. And well, the purpose, perovskites are actually quite exciting when compared to conventional semiconductors that are out in the market today. They pretty much have a high conversion rate, and that's sort of the purpose, is just to try to find which structure will make it work best. And